We're going to look at the limit of a sum today, and our summation goes from I is equal to 1 to n of 1 over n times I over n quantity squared. So as we go through this, the first thing that we are going to do is we're going to take the squared out here and we're going to distribute that on the top and the bottom of our fraction, making it a little bit easier to work with. You'll notice we have two letters that are changing in this particular problem, which makes sums and limits a little bit more tricky. We have our n on the outside going to infinity, so that number is changing. And then on the inside, we have I starts at 1 and goes all the way up to n. So that is also changing. The first thing that we're going to do is we're going to try and get rid of that sum. So we're going to do a couple steps here to make sure that that sum just kind of disappears and we don't have any i's and we're just left with n's here. Now, what we can do at this point, now you'll notice that we have a fraction. We've got an n squared and we've got an n. So let's actually smush those together. I'm just going to bring that n to the outside. I is equal to 1 to n, 1 over n cubed times I squared. And when we have two things that multiply inside, so if you have a summation of some sort and you have a constant times some function of I, or some, I should put AI in there. Let me actually do that. Um, some sort of summation depending on I is equal to 1 to n, we can actually pull the constant all the way to the outside of our sum. This is one of those nice tools that we have, and it's still going to be equal. So that is the rule that we're going to use here. We're going to pull that 1 over n cubed to the outside. And that leaves us with the sum I is equal to 1 to n of I squared, which brings us to our next nice little piece of information. So when we have the sum of I is equal to 1 to n of I squared, if you do a counting argument, and we're not going to go through the details here, uh, because I want to make sure we just keep on clipping along to get our solution. You can find this somewhere else in a textbook. I might even do this as a separate video at some point. We know that that sum is going to be n times n plus 1 times 2n plus 1 divided by 6. And like I said, it's a counting argument, very doable. So what we can do is we can substitute our summation there with the other side of our equation, and that is going to give us everything without an I. So now we have the limit as n goes to infinity, 1 over n cubed times n plus 1, 2n plus 1 divided by 6. All right, now we're at the point where we want to reduce things. I'm going to do one thing right off the bat to make this a little bit easier. You'll notice we have an n hanging out of front here, and we can cancel it with one of the n's on our denominator right away. And that's going to make our lives a lot easier. So this is going to give us the limit as n goes to infinity, n plus 1 times 2n plus 1 divided by 6. And I'll put that in there, 6n squared. We'll smush those two together. Now what we can do is we can distribute and multiply our numerator all the way out. So don't forget, it's going to be a little bit of work, but we can do that. We end up with 6n squared on the denominator. The numerator ends up with 2n squared plus n plus 2n plus 1. I'm going to rewrite that once more because we can put together those two middle terms to get us 3n plus 1 over 6n squared. Now, here's a little bit of a tip. If we have same degree on the top as on the bottom, then your limit is the ratio of the leading coefficient. And by leading coefficients, we mean the number in front of the n squared in this case. So it's the largest degree. And if you enjoy tips like this, subscribe. I'll be doing Calc 2 problems all fall or all spring. Calc 1 in the fall, Calc 2 in the spring. Okay, so why is that the case? I'm going to go through and show you why that is always going to work out. In this case, if we wanted to end our solution right now, we just say, it's 2/6 or 1/3. In this case, the reason why it's the coefficients, the ratio of the leading coefficients is because we can pull an n squared out of our numerator. And if we pull an n squared out of every single term on our numerator, and we pull an n squared out of our denominator, now we cancel those n squareds. Notice what's left. We have the 2 on top, we have the 6 on the bottom, but we have a 3 divided by n, which goes to 0 as n goes to infinity, and 1 over n squared, which also goes to 0 as n goes to infinity. So what is left over are 2/6. In other words, 1/3, which is our solution for this problem. Thank you for listening.